everyone, welcome to the YouTube channel of YourPedia Engineering Career Point. So I'm Vineet Sharma, your mentor of mechanical engineering here. So as you know, the Oil India has announced the vacancy here, and the vacancies are very good in number. Okay, so there are around 35 vacancies, and we have already started the module for that particular exam here. Okay, so you can join us and just start your preparation here. So basically, in today's videos, I am here to provide you the important questions here related to the thermodynamics, in which I am going to cover only important 20 questions here. Okay, so it will comprise of entire thermodynamics, and for and I will also come up with the different types of subjects also. Okay, with the different questions here. Okay, so let us start with the toward our first questions here. The questions are very simple. Maybe some questions are going to be a little bit difficult or tricky for you, but you have to cover that part in detail also, because as you see, the Oil India Limited as well as the BEML, both of exam are going to be clashing here, are going to be in few months here. So you have to be prepared well for both of these exams here. Okay, now, so let us start this series here. So here we have first question. In this case, you can see in the first question what is given to us: the bulk modulus K of a perfect gas in terms of pressure P in an isothermal process is related by the equation here. Now, first of all, the thing is, what is the meaning of bulk modulus and how do we define it? So just see, bulk modulus is defined as the, I can say, the change in pressure required to create a unit amount of volumetric strain here. Okay, in the fluid mechanics, you also see, you have already seen that bulk modulus and the compressibility, these are the two important parameters here. These are the two important parameters which are reciprocal to each other here. Okay, so in this case, we can define the bulk modulus as, bulk modulus as dP upon minus dV upon V here. So I can say the K is going to be equivalent to minus dP divided by dV upon V here. So that is a formula here simply. So if you are having a perfect gas, okay, of a defined mass, let us space M, in that case you can see the mass is constant here. Okay, and what we are doing, we are carrying out the isothermal process in the case of a perfect gas also. Now, in the case of an isothermal process, we know that pressure and the volume product has to be remain constant. Okay, so if I just simply differentiate this term, you are going to see that it will be written as PdV plus VdP equal to differentiation of constant, and in this case, PdV plus VdP is going to be written as 0. So, okay, so correspondingly, if you just find out the value of the by rearranging the term, you will find that PdV is equal to minus of VdP here. Okay, and after further simplification, I can write P is going to be equivalent to minus VdP upon dV. Okay, and that is having the same form as the bulk modulus here. So therefore, I can say for the isothermal process, the value of the bulk modulus is nothing but it is equal to the pressure of the fluid here. And similarly, if you are carrying out the process as an adiabatic process, in that case, the formula is going to be equivalent to P multiplied by gamma into P here. Okay, so just understand that part. So here the option number B is going to be the correct answer of this question here. Okay, so that is a very simple case which you have to remember. Now the next question which we have is the next question. The specific heat of a diatomic gas at a constant pressure is given by. Okay, so we have to find out the specific heat at a constant pressure. Okay, in terms of universal gas constant and in terms of molecular weight of the gas here. So first of all, just see, here we are also dealing with the diatomic gases here. Okay, here we are also dealing with the diatomic gases. So first of all, just see, we know that the value of the specific heat at a constant pressure is given by gamma R upon gamma minus 1. That is the case. And in this formula, I can say that for the diatomic gases specifically, the value of the gamma is nothing but it is equal to 1.4 here. If you are dealing with the monatomic gases, in that case, the gamma is going to be equivalent to 1.667. If you are dealing with the I can say different gas here, okay, or exhaust gases here, then the formula is going to be 1.33 something. So if you just put the value of gamma as 1.4, you are having a formula of Cp as 7 by 2 into R. So here R is representing the characteristic gas constant, and we know that the relationship between the characteristic gas constant and the universal gas constant is equal to this one here. Okay, So therefore I can write the form of the Cp is going to be written as 7 by 2 into R by M here. So okay, so option number C is going to be the correct answer here. Don't get confused, here R is representing the universal gas constant. Here in this case I have assumed the R as a characteristic gas constant here. Okay, so option number C will be the correct answer. Next part, a well insulated vessel containing the air is heated to double the pressure and temperature. Containing air is heated to double the pressure and temperature 150% in excess of the initial here. The amount of air that leaked is, so first of all let us say we have a vessel in which pressure is P1, volume is V, okay, and temperature is T1. Now the air is heated in such a way that the pressure is now twice of the initial pressure here, okay, and correspondingly you can see the volume is going to be remain same, it is not changing here because we are dealing with the well insulated vessel here. And the next part is the temperature is 150% of the temperature is 150% here now. So I can write 1.5 of the T1 here. Now we have to find out how much amount of air has been leaked here in this case. Okay, so first of all just see in this case we don't know that whether the vessel is a rigid one or not. So there may be a chance that the volume may get changed here, okay. So here we have to find out the amount of air. We can find out the amount of air that has been leaked by finding out the change in volume here, because I cannot say a comment on the volumes here because it is not mentioned that it is a rigid vessel here, okay. So here you can see how can I write down the relation here first of all, okay. In this case, as we know, for an ideal gas here, PV upon T is going to be equal to constant here. So I can write P1 V1 upon T1 is equal to P2 V2 by T2 here, where P2 is twice of P1. We don't know about anything about the volume here. T2 is 1.5 into T1 here, okay. So if you just simplify it, you are going to see that V1 is coming out to be around, how much value you are getting here, 4 upon 3 into V2. That means volume is decreasing here, volume is decreasing, okay. So by how much value the volume has been decreased, so we can calculate it as V1 minus V2 by V1 here. So you are going to find by 0.5. So by 0.25 the volume has been changed, okay. So that means the amount of volume by which it has been changed is representing the amount of air that has been leaked from the system, okay. So therefore the option number C is going to be the correct answer here in this case. So I hope it is clear to you. That is a very simple case, okay. Just find out the initial volume and final volume and get your final answers here. Next, in macroscopic approach in the study of the thermodynamics, the structure of the matter is taken into account, okay. First of all just see, whenever you are studying the thermodynamics, there are two type of approaches. The first one is a macroscopic and the second one is a microscopic. In the case of a macroscopic here, you are not dealing at the atomic or molecular level here. You are just finding out the average values of the coordinates here, or I can say the properties here, okay. So I can say the structure of the matter is going to be taken into account here. Yes, it is a correct statement here, okay. Next part, just give me a second. There is I think there is the structure of matter is, this is the second statement. I think the structure of the matter is not considered here, okay. And this is a third statement here. Only a limited number of properties are used to describe the state of matter. The fourth one is the value of the property needed for the description of system cannot be measured here. So you can see statement number 4 is the incorrect one here, okay, because we can simply measure the values of the properties here. We know the value of the pressure, volume as well as the temperature. Third, only a limited number of properties are used to describe the state of matter. That is also an incorrect one here, okay. So basically here in this case the individual molecular behavior is neglected, but the overall structure of the matter is taken into account here, okay. So statement number 3 is also incorrect. Statement number 2 is also incorrect here, okay. So only the statement number 1 is the correct one here. So option number A will be the correct answer of this question. Okay, so that is a very nice question here, just making sure you clear that concepts here. So the next part is general energy equation for the flow process is given by here. Okay, so now just see what is the meaning of flow processes here. Flow processes simply means we are dealing with the open system. In the case of open system, there is a continuous flow of the mass as well as there is a continuous flow of the energy also. Okay, so in that case we have to consider the enthalpy, we have to consider the kinetic energy, we have to consider the potential energy also. So option number C is the correct one here. Okay, next, during the charging of a tank from a pipeline, the temperature of the fluid T is in the pipeline here. The final temperature in the tank will be multiplied by. Okay, so here what we have, here we have a pipe which is being connected by a container here, and I am assuming that initially it is evacuated. Initially it is evacuated here. Now what we are doing, we are filling the tank with some air, okay, or with some fluid which is maintained as a temperature T in the pipeline here. Now what will be the temperature inside the container, we have to find out. The value of T1 we have to find out. Okay, so just see, that is a case of an unsteady flow, because in this case the mass and the energy is continuously changing here. Okay, so you have to do the mass balance as well as the energy balance also. So if I just do the mass balance here, in this case you are going to write M entered minus M exit is going to be final mass minus initial mass here. Okay, and in this case there is no mass exit, there is no initial mass, so I can say the mass entered is going to be equivalent to final mass. That is the first case here. Okay, and if I just do the energy balance also, I can write energy entered minus energy exit is equal to final internal energy and minus initial internal energy. Why I am writing the internal energy toward right side? Because it is representing the energy of the fluid inside the container. And why I am writing the in the form of enthalpy on the left hand side? Because here we are dealing the energy which is flowing into the system or out of the system here. Okay, in this case there is no mass, so internal energy is going to be 0. There is no energy exit, it is also going to be 0. So mass energy entered can be written as mass entered multiplied by enthalpy. Final internal energy can be written as final mass multiplied by Cv into final temperature. Okay, so here just right now we have seen the final mass and the entered mass are same, and the enthalpy is written as Cp into T here. So therefore you can see that T1 is nothing but it is equal to Cp by Cv multiplied by T here. Okay, so by which parameter you have to multiply the T in order to get the final temperature? That is Cp by Cv here. So option number C will be the correct answer here. Okay, so that is the case you have to remember. Now the next question, consider the following statement. In which of the following devices the equation dq equal to du plus pdv is not applicable? Okay, so first of all, this equation, always remember that in the first law of thermodynamics the first term is representing the type of system here. So if a du is given to you, that means it is a closed system. If de is mentioned here, it is representing a open system or a closed system both. PdV is given, that is representing a reversible process. If simple W is representing, that it is representing a case of reversible as well as irreversible processes here. Okay, now in this case you can see, in the case of internal combustion engines, whether it is a Otto cycle, diesel cycle, okay, we can use this one here. Why? Because here we assume that each and every process is a closed system here. Okay, in the case of gas turbine and in the case of steam turbine we cannot apply this, because here it is a case of a open systems here. Okay, so and that equation is specifically written for the open system, closed system here. So I can say the option number C. Option number C here. So that is a wrong here. 3 and 4 is the correct one here. They cannot be this equation cannot be applied in this case here. Next part. 1 kg of water at room temperature is brought into contact with a high temperature thermal reservoir. The entropy change of the universe. Okay. First of all, just see. Yeah. So in this case, whenever you when you brought the water at a room temperature with a high temperature thermal reservoir, what will happen? The water temperature will be increased here, and there is a finite temperature gradient present between the system and between the surrounding here, between the water and the reservoir here. So whenever there is a finite temperature gradient and whenever the time is present, in that case every time you have to understand the process is going to be irreversible in nature. Okay, so I can say the entropy change of the universe is always going to be positive here because it is a irreversible process here. So option number D will be the correct answer here. Okay, now next part, the entropy will usually increase when a molecule is broken into two or more smaller molecule. Yeah, that is the correct one here because entropy is simply representing you the randomness or the degree of degradations here. Statement number 1 is the correct one here. A reaction occurs that result an increase in number of moles. Again, that is the correct one here. Okay, the same thing, randomness is increasing. Process is adiabatic. We cannot sure. Okay, just give me a second. We have to find out the entropy will be increased here. Process is adiabatic. Okay, I will explain you later on. Just see the statement number 4 is process is reversible adiabatic. Just remember that every reversible adiabatic process is going to be considered as an isentropic process. Okay, because in the case of reversible adiabatic there is no heat transfer, there is no entropy transfer involved, and there is no internal entropy generation here. But if we talk about the simple adiabatic process, in that case there may be a chance the process is reversible or a irreversible one. So if the process is irreversible one, even though the entropy is not transferring here, but the entropy generation may take place. So I can say the entropy is going to be increased in the statement number 3rd. A liquid changes to gas, that is a statement correct one here because the randomness is going to be increased due to the, I can say the I can say the weak bonds are basically breaking down here. Okay, so option number C is going to be the correct answer. So that is a very simple case again. Next part, entropy generation can be taken as a criteria to indicate the feasibility of a process. Which of the following conditions are correct? Okay, so we have to mark down the correct conditions here. First, if entropy generation is 0, the process is a reversible process. That is a correct statement because there is no dissipative effect present inside the system which is leading to the entropy generation. So that means it is a reversible process. Entropy generation is greater than 0, the process is irreversible process. That is the correct one here. Entropy generation is negative, the process is impossible. Yes, all the statements are the correct one here. That is a very simple case. Okay, option number D will be the correct answer in this case here. Now the next part is the dash corollary of the dash law of thermodynamics, that energy is conserved, is the application of conservation of energy to the closed system. So that is a simple case. The first corollary of the first law of thermodynamics states that the energy is always going to be conserved quantitative wise, okay, but the quality is going to be degraded here, okay, according to the second law of thermodynamics. So here we are having the option number C as a correct one here. Okay, now option number C as a correct one here. Next part, which of the following statement is incorrect here? Okay, the greater pressure difference in throttling, lesser will be the irreversibility. That is a wrong statement here because throttling process itself is a process which is irreversible in nature. So higher the pressure drop, the corresponding irreversibility is going to be very, very high here. Okay, A is a wrong one here. The primary source of internal irreversibility is power. In power is fluid friction. That is the correct one here. The greater the irreversibility, greater the increase in adiabatic processes here. That is not a correct one. This is not a wrong one here. Next, the entropy of the universe is continuously on the increase here. That is also a correct statement here. So option number D, option number A will be the correct answer here. Okay, now next part, consider the following statements: slow heating of water from an electrical heater, isentropic expansion of air, evaporation of liquid. Which of these processes are the irreversible in nature? In this case you can see, first of all, constant pressure heating of a gas by a constant temperature source can be considered as a reversible process here. Okay, next, isentropic expansion of air. If we talk about the statement number 2, it can be considered as a irreversible process because I have told you that reversible adiabatic process is always going to be isentropic in nature, but every isentropic process is not going to be considered as a reversible process here if it is non-adiabatic here. Okay, so in this case you can see statement number 2 is a wrong one here. Okay, next, Slow heating of water from an electrical heater, that is completely a irreversible process is here. Evaporation of a liquid from a heat source at the evaporation temperature, that is also a just give me a second. Evaporation of a liquid from a heat source at the evaporation temperature. Even though it is not a reversible process, okay, just see here we have in this question we have to take a lot of assumptions actually, okay, because these are representing, many of them are representing the irreversible processes only here. Let me start again. First of all, just see in the first case, slow heating of water from an electrical heater, that is a case of a irreversible process, it is not a reversible one. Second, isentropic expansion of air. If we talk about the isentropic expansion of air, just see reversible adiabatic is the isentropic one. If it is irreversible, then it has to be non-adiabatic in nature, okay. So it is not clear, so we are not sure about that. Evaporation of a liquid from a heat source at the evaporation temperature only. So here you can see thermal reservoir temperature and the liquid temperature both are same, even though there is no finite temperature gradient, okay. So if the time taken is very very large, where infinite time is there, then we can consider it as a reversible process. If the time is reduced to a finite value, then we cannot say it is a reversible process is here, okay. So till now we can say it is a reversible process only. Constant pressure heating of a gas by a constant temperature source here, that is not a case of irreversible process here, okay, that is a wrong statement here. So you can see out of these three, D is matching here, okay. So they are assuming that isentropic expansion is a reversible adiabatic process. Next case, ratio of PV by RT is representing the, so basically it is representing the compressibility factor here. So compressibility factor is nothing but it is a gas deviation factor here, which tells you about the deviation of a real gases from a the deviation of the behavior of a real gases from a ideal gas here, okay. So option number B will be the correct answer. Next, which of the following can be regarded so that the gas law could be applicable with the commonly encountered temperature limit, okay. So in this case you can use the simple gas law to these gases here, because here we are dealing with the steam, moisture and water vapor. So for that purpose we cannot use the PV equal to MRT relation here, okay. So option number D will be the correct answer. What do you mean by antifreeze chemical here? So from the name itself you can see the substance will basically lower down the freezing point of the water, okay, that are going to be known as the antifreeze molecules here, and antifreeze chemicals here. From the name itself you can see it is not allowing the water to freeze here, so that means it is lowering down the freezing point of the water. Next, region inside the inversion curve is represented by cooling region, heating region, with mu is greater than going to be greater than 0, okay. So in this case, inside the inversion curve, whenever we create a simple TP diagram here, okay, here we have an inversion curve like this one. So inside the region curve we have a cooling region where the value of mu is nothing but it is a slope of dt by dp curve here, it is going to be more than 0, okay. So option number C will be the correct answer. Next, okay, so we have to match these things here, okay. So in this case, how can you match this? Just see the options very carefully. Isobaric thermal expansion coefficient is going to be matched with the 1 upon temperature here, okay. Isothermal compressibility, it is matching with the 1 upon pressure here, okay, because compressibility is a reciprocal of bulk modulus, so you can match it with the 1 by P. Isentropic compressibility, it is a 1 by gamma P here, that is a correct one here, and Joule-Thomson coefficient is going to be 0 there, because it is not matching with the 2 and 3, okay. So I can write option number C is going to be the correct answer. So that is a very simple case only. Now in this case here, dash equation of state for a gas is an improvement of the ideal gas law here, okay. So here dash equation of state for a gas, now we are not specifying that the gas is an ideal one here, it may have a real gas also. So basically for the ideal gases we have an ideal gas law, for the real gases specifically we are using the van der Waals equations here, okay na? So option number D is going to be the correct answer here. So even though we also have a different types of equation, but they are not useful for us because we find a little bit amount of error there, okay. So option number D will be the correct answer. Next question. The thermodynamic parameters are temperature, specific volume, pressure, enthalpy, and entropy. The Clapeyron equation of state define the relationship between the. Okay. Now, what is the closest Clapeyron equation here? That is a very simple case. dP by dt. Okay. Here it is equal to H multiplied by temperature multiplied by specific volume. There is something. So here you are going to see it is basically relating the temperature, pressure, entropy. It is relating the entropy. No, it is not relating the entropy, and specific volume and enthalpy here. So option number D will be the correct answer. Okay, so these are some of the questions which are very important from the thermodynamics perspective here. Okay, so make ensure that you cover up the questions related to the theoretical parts only. Okay, and from the numerical you can just see the numericals are going to be little bit easy for you from this part here. Okay, so just go through those numericals which are very simple, okay, which are directly formula based here. You don't have to go into detail numericals here. That is not so much useful for this particular exam here. For the BEML here, you can do you can practice a little bit high level questions here. Along with that, I have already done the previous analysis here. In that case, the thermodynamics does not find so much weightage here. Okay, so if you are not able to cover up in detail here, then it will be sufficient for you. It will be okay for you. Okay, now, so don't take too much tension for this particular subject here. So that's it for today's class here. So thank you very much. Now we will see the remaining question in the next series here. Okay, now.